Good morning. I am Balannanan from Shandong University in China. This is session C1.2. Our presentation is on a new parameter of geomagnetic storms for space weather applications. This lists the content of our presentation. We begin with a brief introduction. Then we define the new parameter called IPS-DST. Then we show some of the applications of the new parameter and finally discuss how the new parameter becomes better than the conventional parameters for space weather applications. As you know, space weather originates in the sun with an eruption. The eruption emits intense electromagnetic radiation called solar flare and simultaneously ejects solar plasma and magnetic field called, for example, CME. CMEs propagate fast through the interplanetary space as ICMEs. They interact with planet's environment and sometimes affect technological systems. Like Earth's weather, space weather sometimes becomes severe. When it becomes severe, it can cause extensive social and economic disturbances in the high-tech society by damaging utility systems such as electric power grids, communication networks, oil and gas metal pipelines, satellite systems and satellite communication and navigation, etc. For example, the Quebec event in 1989. During this event, over 5 million people in Quebec lost electric power for more than 9 hours. Now imagine an event similar to the famous Carrington event of September 1859 occurring at the present time. It can cause huge damages costing up to 1 to 2 trillion US dollars. It is therefore important to study space weather, identify severe space weather from normal space weather, understand what determines the severity of space weather, and think of how to forecast severe space weather. In this talk, we introduce a new parameter of geomagnetic storms called IPS-DST for space weather applications. The applications include identification of severe space weather from normal space weather, investigation of ionosphere thermosphere storms, and study of low latitude aurora. Now, severe space weather is defined as the one causing electric power outage and telecommunication failure, while normal space weather does not cause such severe effects. Now, what is the need for a new parameter of geomagnetic storms? Conventionally, the intensity of geomagnetic storms has been used for space weather applications. However, while studying what determines the severity of space weather, we realized that the storm intensity is insufficient to distinguish between severe space weather and normal space weather. So we introduced the new parameter called IPS-DST. Now we define the new parameter. This is a geomagnetic storm in DST index. X-axis is universal time, Y-axis is DST values. The geomagnetic storm started at this point. This is the storm sudden commencement. This is storm main phase, and this is the recovery phase of the storm. During the storm main phase, DST starts decreasing from this point, which is called the main phase onset or MPO. From MPO, DST continues to decrease and reach the lowest value called DST min, which represents the intensity of geomagnetic storm. This value has been used for space weather applications conventionally, but we found this was not sufficient to distinguish between severe space weather and normal space weather. So we introduced our new parameter. For defining our new parameter, first we found the sum of the modulus of DST from MPO until DST min. Then we divide the sum by the duration of the main phase from MPO to DST min. That gives the new parameter IPS-DST equal to modulus of DST during the main phase divided by duration of the main phase. Thus, by definition, the new parameter gives the mean value of DST during the storm main phase when main energy input takes place. As you can see, the numerator of the definition corresponds to or proportional to the total energy input, and denominator is the duration of the energy input. So higher the energy input and shorter the duration, the more impulsive its action. IPS-DST therefore represents the impulsive strength of space weather or geomagnetic storms, and hence the name IPS-DST. Now we are coming to the applications of the new parameter. First, we tried the application to identify severe space weather from normal space weather. For this, we considered all geomagnetic storms occurred since 1958. During this period, 5 severe space weather events occurred, which are listed here in red. We also include the famous Carrington event of September 1859. During the period since 1958, over 800 normal space weather events also occurred. So the question is how to identify the 6 severe space weather events from over 800 normal space weather events. This figure illustrates our first step. Here we plot the conventional parameter of the storms against the new parameter IPS-DST of all the storms. Red dot corresponds to severe space weather and blue dots to normal space weather. You can see 5 of the red dots are clearly separated from all the blue dots. That means in terms of the new parameter, 5 of the severe space weather events can be identified, while the conventional parameter DST min can identify only these 2 events. This figure also shows the new parameter is unable to identify this particular space weather, that is severe space weather event occurred on 4th August 1972. We will come to this particular event after one more slide. So here we compare the capability of the new parameter with the other parameters of the DST storms itself. That is the new parameter, duration of the main phase, intensity of the storm, rate of change of DST during the main phase, its maximum value, and solar activity. For this particular figure, we considered only the superstorms, that is with the DST min less than minus 250 NT. We also included the lone intense storm, which happened to be a severe space weather event. Then in this figure, the red histograms correspond to severe space weather events and blue histograms correspond to normal space weather events. Then we arrange the parameters in their increasing or decreasing orders. Now comparing the 5 blocks, 5 panels, you can see that in terms of the new parameter IPS-DST, 5 of the severe space weather events have larger IPS-DST than the remaining blue histograms or the normal space weather event, except this lone severe space weather events, which is a puzzle. Now, when we come to the other parameters, they can identify only 1 or 2 severe space weather event. This can identify 2, this can identify 2. But when we come to the duration of the main phase, there are 4 histograms which are red and they have small duration, that is less than 5 hours, less than or equal to 5 hours. But here we have to be careful. The reason is here we considered only the superstorms, but there are a large number of major storms and moderate storms which have duration less than 5 hours, but they are not severe space weather. They are only moderate or even weak storms. Now we are coming to the lone severe space weather event, which could not be identified by the new parameter. It was a puzzle for the scientific community. The reasons are 2. The first reason was it gives all the other severe space weather events occurred during superstorms, while this one occurred during an intense storm with the DST min only minus 125 NT. Our new parameter is also low with the value of only minus 112 NT. And it was also a puzzle because the fastest solar wind velocity was measured during this event. But it happened to be a moderate geomagnetic storm. Though we realized the problem could be related to the time resolution of the DST data, that is 1 hour. So we went back to the original magnetograms of the DST stations. At 2 stations, we got good quality magnetograms at Kokioka and San Juan. Then we rescaled the magnetograms at 5 minutes intervals, and then we calculated the H value. This shows the H value at Kakioka, and this shows the H value at San Juan. You can see this is the storm sudden commencement. This is the main phase onset. This corresponds to the intensity of the storm, that is peak intensity of the storm. Then this range, as seen in the H value, is delta H is equal to 315 NT, but it happened in 45 minutes. This duration is 45 minutes. Or in other words, in 1 hour, delta H would have been 420 NT. At San Juan, delta H was found to be 215 NT in 40 minutes, or in 1 hour, it would have been 325 NT. So from this, we can see the IPS DST would have been less than minus 300 NT. That means it is even stronger, it is even larger than that corresponding to the Quebec event. That we can understand because it is a very strong, very fast solar wind. So the message we give here is we need high resolution DST data for clearly identifying severe space weather events from normal space weather. Now we try to understand whether the mid-latitude index KP and high-latitude index AE can identify the severe space weather from normal space weather when we found their impulsive parameters. For finding the impulsive parameters of KP and AE, we show one example here. The example is for the storm on 29-30 October 2003. All the 3 parameters of the storm are shown here. Main phase is defined with respect to DST. That is the yellow patch. Then for defining the new parameter of KP, we found the sum of KP during the main phase and divided by the duration of the main phase. Simultaneously, for the AE index, IPS AE is equal to sum of AE during the main phase divided by its duration. Now, here we check the capability of the new parameter and the conventional parameter of both KP and AE to distinguish severe space weather from normal space weather. Here also we consider only the superstorms and the lone Indian storm which happen to be a severe space weather event. Here again, the red histograms correspond to severe space weather event and blue cut histograms corresponds to normal space weather events. The values are arranged in their decreasing order in all parameters. The point you can notice here is in all the parameters, whether it is the impulsive parameter of KP or intensity parameter of KP or impulsive of AE or intensity of AE, in all cases, the blue histograms and red histograms are mixed up. That means KP and AE seems to be unable to identify severe space weather from normal space weather. Now we are coming to another application of the new parameter, that is for ionospheric storms. Here first we consider 4 cases of highly super geomagnetic storms. Ionospheric storms corresponding to highly super geomagnetic storms. The storms are listed here, storm days. The corresponding intensities are listed here. They are highly super. And the most super storm was on 2011-2003 with value of minus 422 NT. Their new parameters IPS DST are listed here. The top 2, that is corresponding to the right-hand side blocks B and C, have high value of IPS DST, while the bottom 2 events, that is corresponding to the left-hand side blocks of the figure, have comparatively low IPS DST. Now, what is plotted in the figure is the electron density data measured by CHARMS satellite during its passage from southern hemisphere to northern hemisphere, crossing through the equator. Then the data during the storm is shown by the thick curve numbered 1. And that is compared with the data during the previous quiet period, that is numbered with 3, and it corresponds to the same local time and same longitude. That means same longitude. Now, by comparing the thin and thick curve, we can find the strength of the ionospheric storm. For this particular event, this much is the strength of the ionospheric storm. That gives 69.0 unit. Now, in all the blocks, we made the y-axis equal so that it is easy to compare. Now, for this event, which has high IPS DST, the strength of the ionospheric storm is 42.7. For these two events, which have comparatively low IPS DST, strength of the ionospheric storm is very weak. You can see by comparison. Visually, you can see it is only 14.4 and 11.2. That shows the strength of the ionospheric storm correlates better with the new parameter than the conventional parameter. Here we tried whether the new parameter is better for thermospheric storms. For that, we considered the CHAMP neutral mass density data, that is raw, for the same 4 events, but the data for one of the events is not available. For the other 3 events, the data is available. Out of the 3, the top one, which corresponds to the 30 October 2003 event, has large IPS DST, but the other two, top and bottom, they have comparatively low IPS DST. Now, comparing the figures, you can see only for the event on 30 October 2003, there was a huge surge of neutral mass from both polar regions towards the equator and crossing through the equator. We found such a phenomena happening only on this particular event in the life of CHAM and also GRACE. This also shows large IPS DST associated with strong thermospheric storms. Now we are coming to the statistics of ionospheric storms. That is, statistically, which parameter is better for ionospheric studies, whether it is the new parameter or the conventional parameter. For that, we considered the ionospheric storms measured by the ionosonde at Kokubunchi in Japan for 20 years from 1985 to 2005. During this 20-year period, 191 positive ionospheric storms were recorded. Then we found the peak strength of the positive ionospheric storm for each storm, that is delta NMF2. That is plotted against the new parameter and also against the conventional parameter. Then we found the correlation coefficient. The correlation coefficient is better with the new parameter than the conventional parameter. Now we are trying to study the low latitude aurora, how it is correlated with the new parameter and the conventional parameter. Low latitude aurora means the aurora observed in Japan by Professor Shukawa's optical mesosphere thermosphere imagers. He has measured the intensity of the low latitude aurora at 2 locations in Japan for during 20 geomagnetic storms. In 2005, he reported a paper listing the geomagnetic storm date and the peak intensity of the aurora. Here we show 3 examples: 21 October 2001, 29 May 2003, and 30 October 2003. Out of the 3, the aurora was most intense on this particular night, and it lasted the longest in the night. And for this particular storm, the IPS DST was also very large. Here we try the correlation coefficient of the peak intensity of the low latitude aurora with the intensity parameter and impulsive parameter of the geomagnetic storms in DST index, of the geomagnetic storms in AE index, and of the geomagnetic storms in KP index. That means the left-hand side gives the intensity parameters of the storms in KP, AE, and DST, KP, and AE, and right-hand side gives the correlations with the new parameters in DST, AE, and KP. Comparing the left-hand side block and right-hand side block, you can see that the correlation coefficient is better for the new parameters in all the 3 indices. And the highest correlation is with the new parameter in DST index, that is IPS DST. Thus, we have shown that the new parameter is better for investigating several aspects of space weather. Now we have to understand how the new parameter becomes better than the conventional parameters. For that, I am showing one very important aspect of CME or ICME, that is CME front or CME shock. This is the CME front as seen in the optical observation, and this is the CME front or shock observed by ACE satellite. Velocity suddenly increases to over 2,200 km per second. Then we define the CME front velocity or shock velocity as the difference between the velocity for 2 hours from the start of the velocity increase and 2 hours before the start of the velocity increase. That means this gives the CME front velocity delta V. That is found to be a very important parameter for understanding the impulsive strength of the CME. Now, here what we are showing is the solar wind velocity and IM of BZ during the 4 space weather events which we took for illustration. They are all corresponding to super geomagnetic storms. The right-hand side blocks corresponds to severe space weather events with a large IPS DST. Left-hand side blocks correspond to normal space weather events with comparatively small IPS DST. On the right-hand side, what you see is the CME front coincides with a southward IM of BZ. That is, IM of BZ is southward. In the first case, there is a good coincidence of CME front with southward IM of BZ. Second case also, there is a very good correlation or coincidence of the CME front velocity with strong southward IM of BZ. So what physically happens is CME, that is when the CME comes, the action of velocity and magnetic field will be simultaneous, but for understanding, I consider it separately. First, suppose the IM of BZ opens the magnetopath. Then the CME front impulsively pushes high energy charged particles, a large number of them, into the magnetosphere and ring current. That gives rise to the impulsive action leading to storms, geomagnetic storms with large IPS DST, ionospheric storms with strong positive ionospheric storms, and low latitude, aurora expands and can be observed even from lower latitudes. Now, for the normal space weather events on the left-hand side block, there is a huge impulse. That is, delta V is very, very large, but simultaneously the IM of BZ is either northward or 0. That means when the CME impulse comes, the magnetopath is not open, means the impulse becomes ineffective. So that means it leads to storms with a smaller IPS DST, ionospheric storms become small, but geomagnetic storms can be very large and strong, that is intense. The reason is IM of BZ later becomes negative and remains negative at a high value for a longer period, but it misses the impulse. So to summarize, we define the new parameter IPS DST as the sum of DST, sum of the modulus of DST during the main phase divided by the duration of the main phase. Numerator is proportional to total energy input. Denominator gives the duration of energy input. So it gives the impulsive parameter, impulsive strength. The new parameter is better for a variety of space weather applications. We have illustrated 3 of them. It can identify severe space weather from normal space weather. It is found to be better for investigating ionosphere-thermosphere storms and also low latitude aurora. Now, the new parameter becomes powerful because it automatically includes, though the definition is very simple, but it automatically includes most important characteristics of geomagnetic storms: sudden commencement, total energy input, intensity of the storm, duration of the storm, rate of change of DST during the main phase. All important characteristics of geomagnetic storms are automatically coming into this simple definition. In other words, the definition captures many important processes such as ICME shock, magnetopause compression, total energy input, etc. Large IPS DST corresponds to the coincidence of large ICME front velocity or shock velocity delta V and large IMF base at southward. Now you are welcome to ask questions. Thank you very much.